Unit 2, Kinematics, Displacement Vectors. Today I would like to talk about displacement vectors. And in previous lecture, I talked about kinematics, rotational metrics. And in combination, this displacement vector and the rotational metric in combination will form the important modeling for kinematics. So it is a very important lecture. And we also use this one for the lab material. Displacement vector. In the previous lab, we discussed how coordinate frames rotate relative to each other. The goal was to find the orientation of the end effector of a robot, gripper, paintbrush, robotic hands, vacuum suction relative to the base of the robot. However, when the robot arm moves around the wall, orientation is just half the puzzle. We still need to consider the movement or transition. The end effector change positions as well. To account for this change, the position of end effector, we use what is called a displacement vector, or sometimes we call it transitional vector as well. So usually this displacement vector is important for prismatic joint, Cartesian manipulator, articulated manipulator, and we need to study the transform of coordinate frames. So let's look at the rotational metric again. So basically, a relative rotational metric will have Rmn and rotational frame n with respect to the frame m. So basically, it is a projection problem. So basically, you have vector of m. You also have a vector of n. So n is the frame n vector. It has a projection on m direction. So it will form such a rotational metric. So basically, this is related to the frame n to m. So m is the older frame. Second, let's look at the displacement vector. A vector is a list of numbers. In robotics, we typically use 3 numbers because of the 3 dimensions to represent displacement, for example, in changes in position of one frame relative to another frame in XYZ direction. So actually, because it is 3D, so we use 3 numbers or 3 tuples. We use the following notation to represent the displacement of coordinate n relative to coordinate frame m. So it is a n to m displacement, and we use such a vector form. So let's look at some example. Here actually we have the XYZ displacement. So let's look at the transition. So this one is the vector representation that we talked about in previous lab. So now let's look at transition. If we do not consider the point transition, we consider the frame transition. So here, the original point is here, and your frame m is over here, your frame n is over here. And n with respect to m would have a displacement of a. So here we have a point that it is in the newer coordinate x and y. So basically you have the bigger x over here, bigger y over here. And once you want to translate back to the older x and y, the frame of m, you need to show this one with respect to the m. So we need to have a displacement. So this displacement, actually you have x minus actually will be equals x minus a y, because your point over here, the coordinate over x should be bigger in terms of compared to the x. X is just this portion, right? So you have the x minus a for bigger x, and y would be actually the little y. So we have the x and y be written down as x minus a and y. So we can also write it down as the original y and x will be equals x plus a and y, and we can derive as xy plus a and 0, and we call this one as the transitional matrix. So let's clean it up. Basically, we can represent the newer coordinate that with respect to friend n will plus the displacement matrix, displacement vector of this A0, it will become your original point in the friend M. So friend displacement of A, the move this friend from here to here, equals to the vector displacement of minus A. So for example, here we have a vector like this, right? And we move this way, so it will be like this, right? So this value of the xy, if we have a movement like this way with a transition of A, it is equivalent to your friend go over to here and the new xy. So either you have a minus displacement or you have a plus friend displacement. Two are equal. So anyway, your older friend xm will be represented by your xn plus the an 0. This one is a displacement vector. So we can do displacement vector 1 with respect to 0 would be an 0, something like that. So if we have 3 dimensions, if we have a displacement on a frame, it will be A. If we have a displacement in the y direction, it would be write down as B. Z direction, we will write down as C. So something like this. So that's 3D. So now let's combine the rotational metric and displacement. Now let's look at this rotational and transition frame combination. So let's look at this one. So let's assume that originally our frame is like this. We have a frame 1 with respect to frame 0, right? So basically, the relationship of your x and y should be your x and y plus the a and 0. So this one is a point over here with respect to the frame over here, right? Now, if we have a rotation of theta, So now let's actually assume that we have x and y will be equals your x minus a and y. So this x minus a and y, we make a rotation, and this rotation rotate a theta. So here we have the x and y, and we make a rotation of the theta. So the frame actually rotate by a theta, right? Rotate by a theta, and it respect, this is the x and y value, rotate by theta. So we will get a new set of x2, y2, and that actually is rotate theta. So we can have the x and y should be your x2, y2, rotate minus theta, right? Rotate minus theta. And rotate minus theta in object equivalent to your frame rotate by theta. So basically, we will be able to find out that a combination of these, here we have the xy will be the original x and y's location and rotate by theta. If we are actually in our frame, rotate a theta from here to here. And then we can decouple that by multiplying them, and we will actually see that this y and z, s and y, will be equals a new s and y times r minus theta. and A plus A cosine theta and sine theta. This one is our displacement vector after the frame rotate by theta. So with this information, we can look into the 2 degree of freedom robot arms. So this one, actually, you have a rotational joint over here, and there is a displacement of A over here, and there is another displacement A over here, so A1, A2, and then here you have A3, and you have arm, and then that's A4, and then basically you have 2 rotational joints over there. So the model can be written down as like this, okay? You have A1 as displacement, A2 displacement, A3 displacement, A4 displacement, and totally you have 3 different frames because we have the theta rotate from Z around Z, so these directions over here, same thing over here, these directions over here. And the last one, because you don't rotate, so we keep the same XYZ for the last frame, coordinate frame. So we have the rotational metric like this, and rotational metric of the frame 2 with respect to 0 will be like this. Now let's look at displacement. So displacement, if we have 0 degree angle and the 90 degree angle, the displacement metric will be different, but here we have the displacement of frame 1 versus frame 0. So here, if the theta equals 0, then it will be A2 and 0 and A1. So here the displacement A2 will be here, and A1 will be here. Okay, A1 will be here. A1 show up on the Z direction, A2 show up on the X direction. Y direction, at this direction, it will be none. But if we rotate by 90 degrees, here we have the Z direction, we have A1, and the Y direction, we have A2, and it will be here, it will have Y direction have a 1, here have 0. So here, theta equals 0 or theta equals 90 degrees. You will end up with different displacement vector. So that actually is the theta dependent. So because we have these 2 similar rotational joints and both face up for the rotational direction, so we pretty much end up with similar displacement vector. So now let's look at a Cartesian robot. So Cartesian robot is actually only has the displacement but no rotation. It may have orientation problem, but let's look at this one. This actually is the model for this Cartesian robot. So basically here you can have the extent of D. This direction you have a extension of D2. This direction you have extension of D3. Other than that, the XYZ is actually fixed direction. But we need to work on the orientation problem. So right here, let's look at displacement of the frame 1 versus frame 2. So frame 1, your XYZ are in these directions. So X this direction, Y this direction, Z this direction. Z is the direction that you have extension. So you may have an extension of D1 and a displacement of A1 between the 2 frames. So frame 2, we actually have X direction here, Z direction expansion over here, Y direction over here. So we end up with such a model. So first, we need to work on the rotational metric, and the rotational metric right now only has the orientation change. So we formulate it, that is, X, the red one is a newer coordinate in the blue coordinate frame, and the black one is actually the coordinate frame 0, and we put them in black color. So the rotational metric is like this. Then we have a displacement vector, and that would be A1 plus D1. So our point over here with respect to XYZ, okay, XYZ location over here it need to add the z direction. Z direction actually need to add these two. Okay, z direction. If we consider the z direction value, you need to add this value to there. So it actually add such a amount equivalent to A plus D. Okay, other than that, here we also have a rotation matrix to swap the x1 and y1. So x1, y1 with respect to this 3 direction, that actually is fine. Okay, that actually is fine. Then we plus a displacement over the d direction, d0 direction. So that's a displacement of the frame 1 with respect to frame 0. So here we have a frame 2 with respect to frame 1. So frame 2, basically, you have such extension over here, right? And your frame 3 has a x, y, and z in this direction. Okay, so let's look at it. So over here, you can see like the orientation based on the green one and blue one, we write down something like this, okay? Displacement actually is also in Z1 direction, is A2 plus D2, okay? So basically our blue one, S1, Y1, Z1 can be represented by S2, Y2, Z2 times the rotational matrix plus the displacement. So we have the relationship of a blue coordinate can be defined by the green coordinate. And green coordinate basically can put into the equation for this x0, y0, z0 can be like this. So this one will be replaced by the frame 2 representation. We will end up something like this. Okay. Then we look into the frame 3 with respect to frame 2, and z direction is the same. So no orientation change, but the displacement need to be accounted for. Then we can actually show your frame 3 coordinate times R3 plus D2, 3 versus 2, and it will be something like this because it's an identity matrix, so we can sometimes omit. Other than that, we actually can formulate the x0, y0, z0 coordinate with respect to the original point, and then show it in the displacement vector and the rotational matrix format. Okay, so given any x3, y3, z3, we will be able to find out the s naught, y naught, z naught. Okay, so the displacement vector can be formulated like this. So if you have the displacement with respect to frame 3, you time frame 2 to 1, 1 to 0, you will get that. Okay. You should be able to get the complete displacement term. And you also have the rotational term, okay? Then you make 3 rotation. You can go back to the original point. Now, next one is the articulated robot. Articulated robot will combine the displacement and also the rotational angle. So like this one, we first should formulate all the rotational matrix, and then we formulate all of the displacement vectors. Then we have the combination of all vector and matrix, and we can formulate it like this. So first one, we have rotational matrix of the frame 1 versus frame 0 by the rotational matrix and rotational matrix by the angle theta 1. We should be able to formulate the SYG, X naught, Y naught, D naught with, by the Y1, S1, Y1, G1 with the rotational matrix. So same thing, we can work on the S1, Y1, G1, and then based on the S2, Y2, G2, and the rotational matrix and orientation matrix. So by doing this repeatedly, we will be able to come up with the overall vector, and the result will be something like this, okay? And we can put this formula into the Python program and then do simulation. So this chapter, we introduce you about the rotational matrix and in combination of the displacement vector, and it will be used to fully model the transformation or displacement of your vectors. and we show you the combination of the formula will be something like this, and we can put that into Python for simulation. Okay, thank you. Bye now.